this hole. Okay, but how do we, which half edge do we consider? Okay, so be very careful here. Okay, if we are going to point to the boundary of a hole, it is going to be clockwise. If we consider the boundary of a face, the outer boundary, then it's going to be counterclockwise. Okay, so look at here, okay? So E11, you can see E11, E11 here. So you can see for F1, this is the clockwise, right? This is clockwise direction. So this represents the hole. But for F2 doesn't have a hole. The inner component will be new. It doesn't have a hole in the. But for the boundary, outer boundary, it's going to be E41. E41 is counterclockwise direction. So this is not arbitrary. It's not arbitrary. The counterclockwise direction means it's the outer boundary. The clockwise direction means it's a hole. Okay? And then we have this A half edge. Okay, we can see for each half edge we have the origin, we have twin, we have incident, base, net, and base. Okay, I think I'll not go into detail of each. But one thing you need to be careful to take a look. The incident base, okay, the incident base is not obvious. It's if you try to look at this half edge, it's on the left hand side. Okay, and also the net period are not obvious either. Okay, they will share the same incident base. Okay, so just want you guys to be aware of that. Okay, so that's it. So let's continue our discussion. Okay, so that's the basic idea of doubly connected HV. Okay. Now, okay, we want to consider, okay, because now we are going to model each map as a subdivision, which is represented by the doubly connected HV. Right? So the problem of overlaying two maps becomes overlaying two subdivisions. Okay, so given two subdivisions, S1, S2, of course, each of them will be represented by doubly connected edges. Okay, so we want to compute a doubly connected edges for the overlay of these two subdivisions. So you can look at this feature. Okay, on the left hand side, okay, the solid point represent solid point, solid line represent one subdivision, and a hollow point and the dotted line, okay, represent another subdivision, right? And then when we consider the overlay of these two subdivisions, you will find out that, okay, the intersection becomes the vertex, right? The intersection becomes the vertex. And this will be the overlay of these two subdivisions. And we need to find out the data structure, the doubly connected HV for this S1, S2 overlapping S1, S2. How do we do that? Look at here. The additional vertices that we have to add happen to be the intersection of some line segments, right? Right? Is this sentence sounds familiar to you? I hope, because we spent like 2 hours talking about intersections of some line segments, right? Today, not like last week, right? So actually, okay, computing this intersection. It's not new thing, right? We already learned that. And obviously, overlapping two maps, normally you will not see a lot of intersection anyway, right? So it looks like using like the algorithm that we talked about earlier makes sense. Okay, makes sense. Okay. So the problem of overlay two subdivisions is similar to line segment intersection. But of course, it's not just like that. It's not just that. Because we also need to maintain the data structure, right? In addition to adding those intersection points as vertices, we also need to be able to keep track, make sure that all the vectors are in good shape, right? So this is actually more complicated than we may think. So each half-edge vector will become one or several half-edge vectors, okay, after overlay, because one half-edge vector may be separated by the intersection, right? And then it will become like a multiple half-edge vector, right? Okay, so we are going to treat half-edges as line segments and use line segment intersection algorithm to obtain new points that break the half-edge into shorter half-edge. Okay, so I mean, for half-edge, this is okay. Okay, at least for like so the vertex and half-edge bracket can be adjusted accordingly when the algorithm is executed. So this is at least like computing the coordinates of the intersection for the incident edges, okay, as well as the half edge. Looks okay. I mean, for several cases, for many cases, but not for all cases. Okay, let me explain. Okay, and the phase bracket and the incident phase of each half edge will be computed later. Okay, so these two things will become complicated, especially phase bracket, because you can see that, okay, the original phase will be, cut into multiple parts, right? So it's going to become much more complicated. Okay, so let's consider phase bracket with the left. Okay, the left. Let's consider the other side. Okay. Okay. I mean, there are many cases to deal with. Okay, let's consider one of the, I wouldn't say it's most complicated, but I would say it's a more complicated case. The other cases are not necessary, are not any more complicated. Okay, let's think about it. Okay, so say that we try to overlay this solid point, solid line subdivision with this hollow point, solid line. Okay, and it happened to go through. I mean, in one vertex of the solid line subdivision. Okay. And so that like okay, for the original subdivision, original like the solid line subdivision, no additional point need to be added, which is good. Okay, but look at here. Okay, for example, okay, this solid line. Okay, when the next edge, okay, is pointing to here. The next one should go down, right? I should say this one. Okay, counterclockwise. If we go with this one, the next one should go here. I mean, but in the original family, the next one is here, right? So something needs to be changed. Something needs to be changed, right? Okay. Even though we do not add additional vertex, okay, something needs to be changed. And for this one, the original, we only have one half-edge vector. Actually, we have two half-edge vectors, one direction for each, right? But now, because of this intersection, this one will be broken into two parts. So each one will have two half-edges, right? Yeah. So this is that we can try to for example, when this one is broken into four parts, and dealing with breaking this two half-edges into four, it's not going to be an issue. The issue is like the next and its implementation. But as I said, we are going to deal with space and implementation, right? Yes. Don't worry about this now. The issue is the next. The next and the previous. If we can deal with the next, we can deal with the previous, right? Basically, the concept is previous. Okay. So the previously one student asked me, why do we need to be able to work around the vertex for the instant edge? Now we need that. Why? Because you can see that, okay, for example, if you go here, the next will be, you need to go around this vertex, right, in order to find the next, right? Okay, so how do we do that? Okay, so first, okay, for this one, okay, let's use this one again. Okay, let's use this edge again. Okay, for this direction, okay, you will just use the original map, not the issue. Okay, for this direction, it's going to be for this one, it's going to be the previous, the twin of the previous, the neck of this direction. So that's not an issue. Okay, so going, away is not going to be the issue. The issue is this one, center of this point. How do you deal with the neck of this? If you want to say that. The issue is, okay, we need to, try to, for each half edge that incident to this vertex, we need to be able to find the first clockwise half edge, okay, from E prime, okay, where is E prime? Okay, this one. Okay, so we are going to, if this is going toward this one, okay, its next is going to be the first clockwise half edge, okay, and incident, origin from the B. This half edge will be its next. Okay, so same thing. Okay, this one. Okay, you are going to find that the first clockwise. Okay, half edge. Incident at B will be its next, which is this direction, and so on. Same thing. Okay. So you try to do this. Okay, you have to consider all the half edge that origin from this point, and then store them out in the clockwise order in order to find the next, the previous. Okay? So, with this operation. I mean, this operation is a little bit complicated, but this will take how much time? It will take as much time as proportional to the degree of this level. Degree of this level. Okay. So the other operation, other than finding the max, will take only constant time. For example, like breaking this line into half, into two pieces. This is not going to take much time. Okay, the problem is that you have to work around it takes that degree, proportional to the degree of the. Okay, so how about this? Okay, once we are able to determine the previous max, okay, we already solved out. Okay, then the next thing we will consider is the phase break. But the phase break, as I said, okay, this half age, when you work like from this one to next, okay, you keep working, okay, you'll form a boundary, right? But there are two types of boundaries. Remember how I told you? One is the outer boundary, one is the hole, right? Boundary for a hole. Okay, if you look at this boundary from a big picture, one is clockwise, one is counterclockwise. But I probably shouldn't use clockwise or counterclockwise. Why do I say that? Because it could be something like this, very nasty. So you say go counterclockwise too, you go clockwise too, right? So determining, it is counterclockwise or clockwise. How doesn't help? Like if you only look at the region, then just the local region. Counterclockwise or clockwise doesn't help you to determine this boundary is the whole or is the outer boundary. It doesn't help you. Okay, even though from a grander picture, I told you the clockwise means the whole, counterclockwise means the outer boundary. But it's something snappy. Okay, so how do we do it? Okay. The interesting thing is that, okay, we know there are cycles. There are cycles. Okay. So we determine the outer boundary or the whole. So we can just for it. Now we know it's outer boundary, right? So we just when we walk through the vertex in the outer boundary, we can find the leftmost vertex. The leftmost vertex. Leftmost vertex. Okay, if we have more than one leftmost vertex, we use the lowest leftmost vertex. Okay, and then try to identify the two edges that we walk through this cycle. Two edges that intersect this leftmost. Okay, and we consider the degree formed by these two half edges. Okay, if the degree is more than 180 degrees, then it is outer boundary. Otherwise, it's hole. Okay, an example is shown here. Okay, this is clockwise, and the leftmost is here, and this is the degree greater than 180. You can try to draw those nasty examples, and you will find that, okay, this nasty example will not be the leftmost vertex. It will not be where the leftmost vertex happens. It's impossible. Okay? So this is, again, this is the place where I should start and tell you, this is the observation we can obtain from the geometric problem. But I'm running out of time. Okay, I'm sorry. Okay, I'm still yeah. But I hope you get idea. Okay. So once we are able to determine the outer boundary and the face and the hole, okay. But we also need to be able to associate, okay. For example, remember like certain outer boundary or certain face contain some hole, right? Contain some hole. How to know some hole are contained in the face? Once you know which face is outer boundary, you are able to associate this outer boundary with one of the incident edge that work through this side. So you are able to deal with outer boundary. But the issue is the incident face vector that we have. So we need to have a way to do this. How to do that? Okay. How to do it? The hole is inside our boundary. Okay, I'm running out of time, so I'll just tell you the solution directly. But I want you to think a little deeper and after the class, what that means. Because it's a great point. So give me maybe 10 additional minutes and we can after this class. Okay. So you can draw a dual graph. Okay. So for each cycle, you create what should I say, like a node, a vertex or a node. It's a graph. Okay, let's just call it a node. Okay, you know the graph, right? And you have a node on the edge, right? So for each cycle, we create a node. Okay, and if it's like the outer boundary, then you make sure that node is double circle. Okay, and then okay, you try to you can draw an arc, okay, between two cycles. If only one of the cycles is the boundary of the hole, and the other cycle has a half edge immediate to the left of the leftmost vertex of that hole, right? So for example, okay, you just find the leftmost vertex for each cycle, okay, for each cycle, and then you try to draw the horizontal line to to that vertex, and it's going to touch one of the half edge. So it's one of the half edge. And if it touch one of the half edge, you try to associate, one cycle with another by the edge, by arc, or edge, okay. And once you finish doing so, okay, you will find that each connected component of the graph corresponds exactly to the set of cycles incident inside incident to one bit. Let me show you. Okay. So this is the example. Okay. So you can see that. Oh, by the way, I mean when you create a node, okay, we are going to create one additional node. Okay, in addition to, for example, say we have like 5 loops, then we are going to create 6 nodes. So one of the nodes will be the unbounded phase. Okay, so for example, here, okay, you can see we have quite a lot of nodes here. So we have C1, C2, C3, C4, C5, C6, C7. We have 7 cycles. We have 7 cycles. Okay, but we add one more cycle. We even, okay, as I told you, okay, we just need to have a intercept. So you can see C1, okay, and the C even must be the outer, it doesn't have the outer boundary, okay, and the C2 is a clockwise. We can tell it's a clockwise. We can tell, I should say, outer boundary. We can tell it's outer boundary from the previous discussion, right? So we double circle C2, we double circle C5, C7, C4 for the singular region. Okay, and then for the C1, okay, so we draw the horizontal line. It doesn't intersect anything. Okay, so to the left, we try to look for intersection to the left and look for intersection to the left. And you will find that you cannot find intersect anything. So what happens is that in that case, you are going to associate C1 with C2. Okay, and for C3 is this one. Okay, the left more point here. So when we draw a left horizontal line to the left, it's going to intersect with C2. Okay, intersect with C2. And then if you draw for C6, which is the pole, right, and then we draw leftmost, very horizontal line from leftmost. Then it will intersect with C3. Okay, and for the other, there's nothing here. Okay, so after that, for this dual graph, it will show you that C1 is a hole inside C unit, and the C3 and C6 are holes inside C2. Okay, you can use this dual graph to determine, okay, the association between faces. Okay, which is very important. Okay, which is very important. And you can also, label the new face. You have to also label new faces because you need to know which this new face comes from the previous which previous face, okay, in S1 and S2. Okay, so each new face needs to know which old face of the S1 and which old face of S2 contains. So because normally when we do that overlay, actually we need to, that's why when we want to aggregate information, so we need to be able to do that. Okay. So how to check which face of S1, okay, contains a face adjacent to the vertex C? Okay, if we are able to do that, we are able to do the other for S2 as well. Okay. So if V is the intersection E1 from S1 and E2 from S2, so we just check the incident phase of E1 and E2, that's good enough. Okay, but if V is the vertex of S1, okay, so we need to find the phase of S2, okay, which contains V, but this one, okay, we need to do another transfer LV. Okay, so at the end, this is the transfer algorithm, so net overlay algorithm. But I'm not going into the details. The basic idea I already explained. So the time complexity of this algorithm, the concept, okay, remember basically like the adjusting ratio, as I said, it has something to do with the degree of the vertex, right? So actually, it has something to do with the total degree of vertex. So the total degree of vertex of all the vertex is n. Remember, we talked about that, right? And that n is pretty much determined, because, well, we know that n is basically linear to number of segments plus the number of intersections, right? Okay, linear to that. So it's not going to create any issue. It's not going to raise the time complexity. Okay, so the S1 here plans of with compact S1. When I say compact S1, I mean that if the number of vertices, number of vertices for vertices, number of vertices for the half edge, and number of vertices for the face add up. Okay, these three numbers add up, and it will be the complexity of the WB. Okay, so S2, the complexity N2. Then N2 is N1 plus N2. Then the overlay of S1 and S2 is K, N log N plus K log N amount of time. So K is the complexity of the overlay. Okay, the complexity of overlay obviously bound the number of intersections. Okay, so that's it. Okay, and you can also do something like called Boolean operation, meaning to compute the union intersection of the distance of two polygons. Okay, so I will see that. You can, for your interesting, you can check out this yourself. Okay, we are really running out of time. Last one, total assignment. Okay, 5 problems. Okay, 1.1, 1.3 is from the first chapter, and then 2.1, 2.5, 2.6 from the second chapter. Any questions? The due date for the homework is 2 weeks from the time it is assigned. Is that okay? 2 weeks, it should be done, right? Okay, which is next Wednesday. Okay? Any questions? So that's it for today. I'm sorry it takes more than I expected. Okay. So